Okay, again, thanks for your great introduction. Yeah, so I'm going to present about sparsity in neural networks, so mostly in activations, that is feature maps. Yeah, and it's about split computing, which is somewhat similar to what I think Marco already presented, but not really, because we are splitting the neural networks like inside. So yeah, let's head into the motivation. So as you already heard from multiple presentations. Is it on? Hello? Okay, I'll try. It's not too loud? It's fine? Okay. Yeah, so neural networks are increasing in size. You heard that as an example, GPT-3. If you want the highest accuracies in neural networks, you need millions or billions of parameters, even I think trillions I read somewhere. And yeah, but sensor devices have very limited resources. We can't deploy these networks just on the sensors directly. So that is where we can use the cloud to help via, for example, offloading. And here, however, we have to keep in mind that using, for example, wireless, so I'm talking sensor devices, battery-driven even maybe, who use wireless. Yeah, like transmitting data directly to the cloud via wireless is very expensive. So we have to keep latency and energy in mind. And what we can do is we can use split computing. So assume we have like some simple network. We can split it basically at some certain hidden layer. And what we then do is we kind of do some part of the inference on the sensor node, and then we transmit the intermediate results to the cloud and kind of do the rest of the inference there. And why do we do that? Well, it reduces some load on the server, so we distribute some load. It is slightly more privacy aware, but obviously not private, in the sense like federated learning or something, for example. And we can also even reduce network communication. So let's take a look into these intermediate outputs. So this, as an example, is a ResNet 50 trained on a Cipher 10, so very over-provisioned network, obviously. But we can see that here, for example, like the majority, so this is split at some random hidden layer, basically, inside the network. And we can see that most of the activations are close to 0. And also, if we look at it into the feature maps, there's like a lot of feature maps that are entirely black. And basically, we don't need to transmit these. And they're easy to compress, obviously. So what did we do? We basically analyzed sparsity in individual layers. So that is activation sparsity, which is the individual values inside of feature maps, and also kind of feature maps as a whole, so these entirely black feature maps. And this is basically a guidance to kind of help where do you want to split a network to kind of reduce the amount you have to transmit. And then we apply dynamic pruning, so dynamic activation pruning, and also feature map pruning, so once removing individual values and then removing entire feature maps, shows like the potential for compressing data using these techniques. So how does the system kind of work? We have a sensor, we have like the first part of the network, we get some input data, some sensor data, and we do part of the inference. And now we have like some intermediate activations. And these are feature maps. And now we kind of have our dynamic pruning step. Doesn't matter right now how this works exactly, it's simple, but I'll explain it later. And we kind of remove some values and decide to only transmit certain other values. So we remove some values, we only send these values that live throughout the pruning process to the server. And there we kind of reconstruct the shape of the values to do the rest of the inference on the cloud or the edge or whatever. And then what kind of pruning process, well, yeah, like activation pruning and feature map pruning, like how did they actually work? So given some sample feature maps, we basically just prune according to threshold right now. So this is a very simple method. There's the activation pruning. So given a certain threshold, we just look at each individual value and then decide whether we want to send it or not. And the same can be done on a feature map basis. So given a certain metric, so in this case, for example, the mean, we kind of get like a representative value for each feature map, and then again decide to prune these. Yeah. And important here is obviously to know that we are not removing statically, so we are based on each individual sensor input, we have to recompute these masks essentially, which we want to transfer. So this is the big contrast to the conventional pruning, where we also look at weights, for example, that are obviously static during inference. Now, if we look into the first few layers of a ResNet 50, so these are like the first layers, and the bottleneck is a bit abstracted, obviously. Yeah, we kind of look into the activation values, and here we can kind of see the histogram of activation values after this, yeah, third layer, I guess, after the max pruning layer. And essentially, in this case, we have 12% of all of the activation values are inside of this first bin. So basically, between 0 and 0.5, 0.05. This amounts to 94 kilobytes. So we still have a lot of data to send in this case. And yeah, one layer later, so after the residual bottleneck, which is more than one layer, but we don't want to cut inside of the bottleneck, we have, relatively speaking, way more zeros now, so way more sparsity. However, we also have a lot more data. So now we are at 3.3 megabytes. So while we suddenly have more relative sparsity, the absolute amount is still not that great looking. So if we were to just split based on this, we would rather choose this point. So yeah, now we kind of employ this dynamic pruning. So in this case, activation pruning first, so individual values again. And we use the same 2 points I just showed. So this is called bottle 1, so after the bottleneck block, the residual bottleneck. And we can see that if we just apply basically without doing anything else, we kind of see that we can drop quite a few values. So you can see there's a lot of potential for reduction in size compared to the original size. And also for reference, it's a ResNet 50, so the original accuracy is about 76%. So that is kind of the baseline as well. And if we do the same in the layer beforehand, so after the max pooling layer, it looks like that. So we already have less amount of data because it's a smaller layer in a sense. But in this case, actually, it hurts even more to start dropping these small values. And basically, the summary is, yeah, we can technically reduce up to 70%, but going below 700 kilobytes starts to hurt a lot. What we can do, however, is we can also do it now with training. So during the training process, we just employ the dynamic pruning, nothing else, just kind of like dropout, you could say, I think. And what we see now is that actually the network is able to cope with it. In this case, we can see that the drop-off doesn't really exist anymore in the same sense. It's a way more graceful decay as well, I would say. And the same is true for the residual bottleneck. So in this case, actually, it doesn't make any difference whether we choose the bigger or the smaller layer. Yeah, in this case, we actually can reduce up to 93% with a maximum loss of 1 percentage point. And yeah, going below 200 kilobytes starts to hurt. And now if we do the same for the feature map tuning, so I showed the completely, entirely black feature maps in the beginning. If we try to prune them, like how does that work? As a heads up, obviously, this is like a way more, yeah, it's not so fine-grained, obviously, so it's going to be worse. So yeah, you can immediately see it's not as great anymore. So the drop is much earlier. I think before we had 700 kilobytes as like the cutoff. yeah, now in this case, we can kind of reduce like 10–20% of the data, and that's about it. And for the max pooling layer, the advantage is it has less data, so it's kind of better in this case. But without training, it's not really that great. And if we now do it during training again, it works better, but it's obviously not not good compared to the individual activation pruning, which makes sense. And in this case, for both, it kind of works similarly good. It's much better than without training, obviously. But we can't reach this like 200 kilobytes, for example, or less than that using just this technique. And so what are the conclusions? So basically, we kind of show that there's certain sparsity in individual layers in neural networks, up to 48%, depending on where we look. And if we use this dynamic pruning, we can kind of slightly more efficiently split these neural networks and reduce the amount of data we have to transmit. However, this feature map pruning is probably not the best prospect. So it is obviously a bit easier to use. You don't need to keep track of where each individual value was to reconstruct the shape on the server side. But it just is not that powerful. And as for future work, we kind of want to analyze also like impact of sparsity inducing techniques. And another big thing is kind of the effect of quantization and encoding schemes or other compression schemes to combine them. So there were like, I did some early tests regarding quantization and encoding, and we can push it down quite a bit more, but I haven't fully evaluated it yet, so there's no actual numbers yet. With that, I'm concluding my talk, and I'm happy to take questions.